Alright guys, people are like painting my hallways, so the air quality is really shitty right now, but we're just gonna push through anyway and get this linear algebra done for the day. So before I recall what I studied and learned yesterday, I'm gonna go ahead and jump into Anki and see if we got any flashcards. We do not. Very cool. All right, so what did we learn about yesterday then? Well, we learned systems of linear equations. We would have finished a section called linear equations. Then we would have started a section called linear systems of linear equations in 2 and 3 unknowns. All right, when you got 2 unknowns, you're basically a line. You're looking at two-dimensional space when you have 2 unknowns. When you have 3 unknowns, you're looking at 3-dimensional space, etc. The pattern continues. Right. When you've got the solutions in the form of S1, S2 in parentheses, that's called an ordered pair. When you got 2 unknowns, 2 solutions. When you got 3 solutions, it's called an order triplet. When you've got n solutions, it's an ordered n tuple. I think. What else what do we need to think about here? Right, when we're talking about having more than 2 systems of equations, well, the solution with 2 unknowns is basically there's 3 options. It can either be 1 solution, infinitely many solutions, or no solutions. Actually, for all systems of linear equations, that's the case. When we have more than 2 linear equations, we're basically looking for the intersection of all the equations. So where's the point or plane or whatever it may be in which all systems overlap or intersect, I should say. All right, I think that is pretty much the main stuff. This air quality, I'm telling you, is very bad. Right, okay, consistent linear system and inconsistent linear system, 2 more vocab words. A consistent linear system has 1 or more solutions. An inconsistent linear system has no solutions. Okay, we also read about that linear system notation in which the constant is like a subscript I subscript j, or a subscript ij, in which the I tells you which linear equation is 1, 2, 3, 4, etc. And the j indicates which unknown the constant is attached to, essentially. All right, yeah, that's really all we did, apparently. Yeah, that's all we did yesterday. So we'll continue reading, and then I'll go ahead and recall when I feel appropriate. So I'll talk to you in a second. All right. Okay, so we just finished the section called linear systems in 2 and 3 unknowns. And so basically right here I found 4 ways of solving linear systems. Classic substitution, in which you basically solve for 1 variable and then plug what that variable is equal to in the other equation. Elimination, where you basically add or subtract the equations in order to eliminate one of the variables or the unknowns. 3 is by graphing, so you just simply graph them and find the intersection point. And then 4 is by inspection, in which you inspect and see if the equations are just multiples of each other. And if they're multiples of each other, there's going to be infinitely many solutions. So we worked through 4 examples right there, solving 4 different types, or four systems of linear equations. One that had one solution, one that had no solutions, and 2 that had infinitely many solutions. When you use the way you'll know there's no solution is you'll have a statement that's just mathematically invalid, whereas where you have infinitely many, you'll have a statement that's just true, like 0 equals 0 or 6 equals 6 or whatever that may be, with no variables or unknowns within it. And then they talked about this way of solving for infinite solutions with linear systems with infinitely many solutions via basically parametric equations. So parameter is this arbitrary value. So what you do is you solve for one variable and then assign the other variable an arbitrary value, such as t, and then you basically say that statement and then the definition of the parameter, so like y equals t, and then those are parametric equations, and then you can just plug in arbitrary values in for that that parameter, solve, and then you'll get ordered pairs or ordered triples or ordered n-tuples, whatever it may be, and you can plug those in and they should satisfy the equations and result in true mathematical statements. And that's how you know when you get a ton of these answers that are all true points or planes or whatever they may be, that you have infinitely many solutions. So really you can have, for all systems of linear equations, you can have one solution, no solutions, or infinitely many solutions. There's no other options. All right, so we're into the final section now of section 1.1, which is Introduction to Linear Systems, I believe. Systems of Linear Equations and Matrices is chapter 1, Introduction to Systems of Linear Equations, right. Yep, so this last section is called Augmented Matrices and Elementary Row Operations. What the hell is augmented matrices and elementary row operations? I don't know. Let's write that down. What are augmented matrices? What are elementary row operations? All right, we've got 3 minutes left, so I'm going to basically read this maybe a paragraph or 2, and then we'll be back to recall and then end the day. So I'll talk to you in a second. All right, wrapping up for today. We just learned what an augmented matrix is. Well, first of all, the more equations you have in a linear system, the more complex it gets, and so computation becomes more complex. So we're basically going to use matrices to solve more complex, like larger linear systems. And an augmented matrix is basically a standardized way of translating a system into a matrix. And so for augmented matrices for linear systems, we're basically following the form of like in the matrix, which is a rectangular array of data, essentially. You're going to have A1, A2, A3, and then, the A's and then B. Yeah. So, and they're going to be, we're going to exclude the variables since they're all linear variables, and we're going to have them in order of 1, 2, 3, 4, 5, and they're all additions. So we're going to have the negative numbers in the matrix. The B is going to be on the rightmost side of the matrix, right? Because we're basically organizing all the linear equations to be in the form of A1 1 A1 2 ... A1 n equals B, and then below that the next equation's A2 1 in x 1 plus A 2 x2 plus dot dot dot, etc. But they're all going to be in the same order with the constants in front of if you line them all up, all the same variables are going to be in the same columns. The b's are all going to be on the right side. The equal sign is going to be right in front of the b. Nothing's going to be on the right side of the equation except for the b. On this side, all the variables are in the same positions. There's all pluses in between, or assumed plus signs in between all the variables and constants. So that's it. Another successful day of learning linear algebra. More progress, more learning, new things to be thought about, and new things that are learned. We are currently page and 3/4, less than 2 pages away from finishing the reading for section 1, and then we'll be into the exercise set, so that will be fun. Yeah. 2 will be all right. Until then, I'll talk to you later. See ya.